So this is enzymes. And just as we know already, enzymes are basically proteins. But of course, not all enzymes are going to be proteins. You have got some which are made up of nucleic acids. What are some general roles? What do enzymes do? Some enzymes are used as biocatalysts. They are going to be able to speed up the rate of a chemical reaction, but they are not changed. All right. Other enzymes are going to be used for diagnosis. If you hear diagnosis, diagnosis is just finding out what is wrong. For example, you're going to go to the hospital, they test you, or maybe they are going to give you, say, some information. A person is suffering from this, he has got a problem with this, a problem with this. What is the diagnosis? What is wrong? What is the condition? That is diagnosis. Enzymes are also used in some foods and beverages, in animal feed, in also pharmaceutics. This has to do with medicines and those things in the hospital, biofuels, and also some household items are also going to have enzymes, washing paste, those things, right? So some other important uses of enzymes, they can be used in analytical tests. For example, people with diabetes. So diabetics will use strips of papers fertilized with aldohexose enzyme. If at this point, if I mention aldohexose, it might not make very much sense, but you are going to understand this. This is just an hexose sugar, which is an aldehyde. So diabetics will use strips of paper fertilized with aldohexose enzymes to be able to observe their glucose levels. Okay. So when the liver is damaged, or when the liver has got a disease, this enzyme will be able to leak into blood. And so when you test the blood and then you see this enzyme, it will mean that okay, there is a problem with the liver. So that is an analytical test using these enzymes which are involved in the metabolism of glucose. So you have got many other different functions like therapeutic accelerators. So you can use enzymes, the use of blood coagulation factors. Now, coagulation is clotting, okay? Clotting. So you can use blood coagulation factors to treat bleeders disease. If someone is bleeding, you can use, in your blood there are some we call them clotting factors. These are proteins which will make your blood to clot. If you injure yourself, blood stops coming out because you have got clotting factors. You also use these enzymes in the manufacture of drugs. Okay. Now let's talk about properties of enzymes. Enzymes are biomolecules that affect the rate of a chemical reaction. We know they are not changed. All right. They are not changed as the reaction is happening. With the exception of a small group of catalytic RNA molecules, all enzymes are proteins. And this is how biochemistry comes. They are going to get this statement and say, all enzymes are proteins, true or false. Or they'll just say, with the exception of a small group of catalytic dash, all enzymes are proteins. And then they'll put different options. So enzymes can be RNA molecules or can be proteins. Take note of that. In a chemical reaction, enzymes are not altered. Okay, they are not going to be changed. Another property of enzymes is that they have got high specificity in both the reaction they catalyze and the choice of substrate. And they only work for some chemical reactions and they only work on some substrates, not everything. You know that from the lock and key, right? And also from the induced fit theory. This is what you are just from doing in NS. Examples of some enzyme specific, you have got subtiles. Subtiles will be able to break any peptide bond. If you just hear the name subtile, think of proteins. These will be able to work on proteins. Now you know that proteins are made up of amino acids. For you to break one a bond in proteins, an amino acid is connected to another amino acid by a peptide bond. So the enzyme that can break that bond, apart from peptidases, you also have subtiles. You also have glycosidases. These ones will break a glycosidic bond, and you are more likely to find this in your test one. Almost all test ones, this one has been coming. Lipases, okay, lipases also will be able to attack triglycerides. Now look at this. A triglyceride is a lipid. It's made up of three fatty acids and a glycerol. That's a lipid. So the enzyme that should break down a lipid is a lipase. That's why triglyceride molecules are going to be cleaved by lipase. So these enzymes are going to be relatively specific. Okay, relative specificity. And then you have got also trypsin. Trypsin will be able to break down the carboxyl side of lysine and arginine. Trypsin is also an enzyme which will break down bonds in amino acids, but to be specific, you have got lysines and arginine residues. You also have thrombin. This one will break or hydrolyze bonds between arginine and glycine. These are amino acids. And then you are going to have also urease, which will be able to break bonds in urea or attack urea. You also have carbonic anhydrase. This is a very important enzyme. You'll be hearing it very much, especially in physiology. It's a very important enzyme. Carbonic anhydrase will be able to attack carbonic acid. What happens is that it breaks carbonic acid into bicarbonate and hydrogen ions. You also have arginase, which will be able to attack arginine, that amino acid. Also, glucose oxidase. Okay, this is the only beta D anomer of glucose, so it will be able to break down that. Many enzymes are going to require cofactors. If you hear of a cofactor, an enzyme does not work until it has got cofactors or coenzyme. Cofactors are metal ions, for example, zinc ion, magnesium ion. Every time you hear cofactor, it is a metal ion. But coenzyme, these are what? Organic. All right, they are organic. So that's the difference. Actually, cofactors are a group of coenzymes. Coenzymes are organic cofactors. Okay. So these are going to be able to bind loosely to substrate or tightly bound. So these can either be loosely bound, okay? These same either cofactors or coenzymes, they can be loosely bound and you are going to call them co-substrates. Or they can be tightly bound. So tightly bound coenzymes or cofactors, they are known as prosthetic groups. These are some examples of inorganic uh, cofactors that you need to know. So I've got copper and where they are located also. So copper ions, these are located in cytochrome oxidase. That is the enzyme where you can find these as cofactor. I have seen in some exam questions where they've just asked, which of the following is a cofactor for pyruvate kinase? So you can see pyruvate kinase is potassium. Some of this you just understand them because as you go on, because you are going to be looking on each topic, you look at one enzyme and then you also understand its cofactor. Okay, but you can also get to look at just look at some so that you can at least not be so much behind. You look at this table. Okay, also this one, you have got some coenzymes and also their precursors and their deficiency diseases. Now this one, please, you at least know, please know. So for example, I've got a coenzymes here. You have got coenzyme A, coenzyme K. You can see where it comes from. But my interest is in the deficiency. But you need to know the coenzyme, the precursor, and also the deficiency. They can get any one of these. For example, coenzyme A will give you dermatitis if it is not there. This is just a problem with the skin, right? Let me go to something else which also apart from coenzyme A giving you dermatitis, a problem with the skin, you also have pyridoxophosphate, which is also giving you dermatitis. Which one also is very common? There's a question. Yes, Messi. Your hand is up. Okay, a precursor is where something comes from. So for you to form coenzyme A, it needs to come from pantotheric acid. That is where it comes from. That's a precursor. Okay. So what I want to take note especially is the definitions for beriberi and pellagra. You can see NAD positive and NADP positive. These ones come from niacin. That's their precursor. If NAD positive and NADP positive are not there, they are going to result in pellagra. And then you also have thiamine pyrophosphate. Thiamine pyrophosphate is a coenzyme which comes from thiamine, which is vitamin B1. They can actually ask you the deficiency of vitamin B1 will cause a lack of what coenzyme. So if you don't have vitamin B1, you are going to lack thiamine pyrophosphate, and it means the condition you are going to have is beriberi. Take note of this at least, okay? Pellagra and beriberi, and also anemia. If you don't have tetrahydrofolate, which comes from folic acid, you are going to have anemia. So just try to look at this table, especially this one for pellagra, beriberi. Please know them. Also, anyway, at least know those today. For these other ones, if you cannot know them, be knowing them each a day. Okay, so this is what we are from talking about. Dermatitis is just the inflammation of the skin. Pellagra is a syndrome due to niacin deficiency and is going to be marked by dermatitis on parts of the body exposed to light. Okay, beriberi is a disease that is marked by cardiac pathology. There is a problem in the function of the heart. Scurvy is marked by anemia, spongy gum, your gums, Pernicious anemia, this is uh, an autoimmune disease, meaning that your body is destroying itself. So you end up not having enough blood in your body or blood cells. Now, let's look at the international classification of enzymes. If I go to America, if I go to UK, if I go to South Africa, I mention this enzyme. How are they going to really know? Just like we have in organic chemistry, we have got the IUPAC naming. So you please, this one you need to know. You need to know. So enzymes can be classified in 6 ways. You need to know the number, you need to know the class, and at least know an example. All right. So number one, the class here is known as oxidoreductase. Number one class, the name is oxidoreductase. So they can ask you, class 1 enzyme is, if you don't know class 1 enzyme, class 1 is oxidoreductase. You can even get from the name oxidation and reduction. So this enzyme is involved in the transfer of electrons. An example is dehydrogenase. And then class 2 enzymes, these are known as transferases. Even from the word transferase, they transfer groups. For example, methyltransferase. Number 3, hydrolases. Even from the word hydrolase, they are going to be able to break bonds. Hydrolysis. Okay, so hydrolysis reactions. An example you can give is which one is this one? Okay, lipases and nucleases. On the examples, you not more concentrate on there. What you want to know is the class and what it does and the number of the class. I will give you a simple mnemonic for you to remember. Othliu. Othliu, that is, let me just write that. This is the mnemonic that helped my friends when we are trying to swatter these. Okay? Othliu. O, oxidoreductase. The T is transferase. The H is hydrolase. And then the first L, just know that The first L should always be a lyase. The last one should always be a ligase. And then you have got isomerase. Isomerase, isomers are just same compounds which look different, right? Those are isomers. So isomerases will be able to transfer groups within molecules to yield an isomer. They'll transfer groups within a molecule to yield an isomer. Okay. And then you have got ligases. Ligases will be there for formation of bonds between a carbon to sulfur, a carbon to oxygen, carbon to nitrogen bonds. And this will be done by condensation reaction, meaning you are connecting these atoms. Okay, and that will be together with it to be coupled to ATP cleavage. So as you are connecting these compounds, you are breaking down ATP. ATP is a form of energy that a body uses. Lyases, these are additions of groups. They are reactions which they catalyze is addition of groups to a double bond. Okay, so these are the classes. And what is even more important is to know that of all these classes, class 3 and class 4 do not require any coenzymes. So meaning that hydrolases and lyases can work without coenzymes, while the rest of these enzymes will be able to work only with coenzymes. That is something that you want to be just next to you. Do we have any question here? Are we good so far? Okay. Now, how do enzymes work? So the way enzymes work is, this is a question which came from in your last year's Bio 1400. I just saw the paper. So enzymes work by lowering the activation energy barrier. You can see the reaction without an enzyme. You have got a very big hill. So for you to be able to climb this hill, it will take you a lot of energy. Actually, it takes more. The energy that enzymes require, or energy that reactions require is the energy for them to move from the beginning to the maximum point there. But now you have lowered the hill, so it will take a little bit of just a small energy for them to reach the hill. Immediately they reach the hill, the reaction can just proceed by itself like that. Okay, so the energy difference between the beginning of the reaction and the maximum point, that is known as activation energy. And then the energy difference between the reactant and the product, that is known as the delta G, or Gibbs free energy. Okay, a chemical reaction of substrate S to form product P is going to go through a transition state. Yes, Modesta. Gibbs free energy is just a difference between the energy of the product and the energy of the reactant. So let's say here where there is product, if you follow, you go to the Y, it is giving you 10. And then on the reactant, let's say the reactant's at 20. So to find delta G will be 10 minus 20. Okay, that is how you find it. Okay, and like that. So some thermodynamics that you have to consider for energy difference between reactants and products, that's delta G. If you find delta G and your delta G is negative, that should tell you that your reaction is hexagonic, meaning that in this reaction you are actually releasing energy. Okay, and every time you see delta G is negative, it means that the reaction is spontaneous, it's happening by itself. When delta G is positive, it means that this reaction is endergonic, you are gaining energy, and that reaction is not spontaneous. If delta G is 0, it means that your reaction is at equilibrium. Okay. So the energy needed to initiate the conversion of reactant to product will be able to determine the rate of the reaction and also affects the enzyme. The energy that is required for you to convert the reactants to the products determines how fast the reaction is going to be able to move. Now, this is not very much necessary, but just something that you can take note of is that delta G is negative 2.303 RT log of K. So delta G is also related to the equilibrium constant. Delta G is going to be negative 2.303 RT log of K. So for example, equation here, calculate delta G for the isomerism of DHAP to GAP. If at equilibrium, the GAP to DAP ratio is 0.45, 0.0475 at 25 degrees Celsius and pH 7. Is the reaction hexagonic or endagonic? Now, if you can look at this reaction, they've told you that this DHAP is going to GAP. So the product is GAP. So if you find the ratio of GAP to DHP, you have got something that is known as the law of mass constant, where that thing that you used to use, we also call it as, what was the symbol you used to use in first year? Okay, the K or just G. K is given by the amount of product divided by the amount of reactants. If you remember, so product is GAP, reactant is DHAP. So we've been given that ratio already. So the ratio of product over reactant has already been given. So delta G will be negative 2.303 RT log of K. So you just substitute R is the universal gas constant, and that will obviously be given. Okay, that is 1.987. You multiply by the temperature, that is 1.987 times 10 to the -3. Temperature is 25 degrees, but you always use in Kelvin, so add 273 to it. And then log of K is given by the ratio of the product over the reactant, but it has already been given there. So you find that your answer is positive. So since the answer is positive, is this reaction endagonic or hexagonic? Anyone to answer that one? Yes, very good. Okay, so that will be the same one with this one, so I don't need to concentrate on that. Now, let's talk about the catalytic or the active site of an enzyme. If you look at the three-dimensional shape of an enzyme, you can see where it is turning like that. That is where you're going to be able to see the active sites. Immediately, if there is a mutation in an enzyme, you just destroy the way this enzyme folds like this. Then you have destroyed that enzyme and it can no longer work. Remember when you are talking about proteins in first year, proteins have got levels of protein structure. I've got the primary level, which just shows the way amino acids are bonded to each other. Secondary level, which can be beta pleated or alpha helix. Tertiary level, which can either be globular or fibrous. And then quaternary level, which is a combination of more than one tertiary levels. So the active site, immediately there is a change you just change the way the enzyme is, you have destroyed it, it can no longer work. Okay. So the active site will be able to take up only a small part of the entire enzyme. So there are two laws, or there are two proposals that propose or there are two theories which propose how enzymes do work. And actually in my exam, this one came in, it was show your work writing. Name the two theories which propose how enzymes work. And as simple as that question, so it's the lock and key and the induced fit theory. The lock and key tells us that a substrate, who each enzyme has got a specific substrate in which it will be able to fit in exactly. Now, the induced fit tells us that actually the enzyme doesn't have to fit exactly with the substrate. You can see this enzyme, it doesn't fit exactly with this substrate. So what happens that the enzyme is going to change a bit its shape in order to fit its substrate. That is known as the induced fit, different from the lock and key. So these are the two theories which propose how enzymes work: lock and key and induced fit. So you don't want, imagine that came in your exam, 2 marks. You don't want to lose that 2 marks. Trust me, it's a lot. Some fail actually with a 49, by the way. Passing here it is 50%, not like main campus in NS where you pass with a 40%. So let's talk about functional and non-functional plasma enzymes, which are going to aid in diagnosis and prognosis. So certain enzymes, proenzymes and their substrates, are present in all types in the circulation of normal individuals. Some enzymes you always find them in you normally at physiological function. Every time you hear of physiology, it means that the way the body normally functions. So some enzymes are always present in the body. Immediately you don't see them, you know that there is a problem because they're always supposed to be there. So those are known as functional plasma enzymes. For example, I've got lipoprotein lipase, pseudocholinesterase, proenzymes of blood coagulation and blood clotting dissolutions. For example, you need some enzyme like the clotting factors. When your blood, imagine you have got a wound, you are cutting your vegetables, mistakenly you cut yourself. You need these enzymes for you to be able to stop bleeding. But imagine you don't have them, it will cause a problem. So those are some examples of functional plasma enzymes. And majority of these are going to be made and secreted by the liver. Okay. They are also others are also known as non-functional plasma enzymes. These ones are going to arise from normal destruction of red blood cells and other tissue. So when you destroy normal red blood cells, those are going to be non-functional plasma enzymes. They are not really that necessary. So what will happen is that when you analyze these non-functional plasma enzymes, the analysis of the presence and distribution of these enzymes and lysoenzymes are going to help in diagnosis. You are going to know that okay, there is something wrong. For example, let's say when red blood cells have been destroyed, you expect to have this kind of enzyme in a certain amount, and then you are seeing too much of that enzyme. You know that there is something that is wrong. Okay. So some enzymes, serum is just we are just talking about blood. For now, just know as that liquid part of blood. Okay, you know that that is plasma. The liquid part of blood is plasma, but you have got some things which are found in that liquid part. So you need to know at least these enzymes. This one, I don't know how, but at least I've tried to simplify it the way I've written my table. You need to know if you find some enzyme like lactate dehydrogenase, creatine kinase, aspartate aminotransferase. These are three enzymes. Immediately you find them more in blood, you know that there is a problem with the heart that is known as myocardial infarction. Okay, the problem with the heart. And this one mostly it doesn't remain whether in test one or in the final exam. So you better know that. And if you see alanine aminotransferase, the condition that you will be able to think about is viral hepatitis. There's a problem with the heart caused by viruses. And then you also have acute pancreatitis, a problem with the pancreas. If you see amylase and lipase, you know, okay, there should be a problem with the pancreas. Okay. What other common ones do they bring very much? Especially this one on top. Please take note of that. You also have hepatoleticular degeneration, we also know as Wilson's disease. The enzyme there, creatine kinase. If you just see creatine, now every time you think of creatine is a compound that is produced in the muscle. So immediately you see a lot creatine kinase, there should be a problem with the muscle, so there's muscle disorder. Please, this table, make sure you drink it. Also, metastatic carcinoma of the prostate. If there's a problem with the prostate gland, just know there's a problem with phosphatase. This one you also understand in anatomy. So, phosphatase is an enzyme that is going to be present in the prostate fluid. So, if you see it very much like that, you know there's a problem with the prostate gland. Okay, so you might have a metastatic carcinoma of the prostate. More I'll concentrate. Know this one on top. At least today, know lactate dehydrogenase, creatine kinase, aspartate aminotransferase. How do you know these things? That is med school now. You need to be sharp in making to my short ways in which you are going to be able to know things. Okay, so for me, I'll just say lac. If I want at the end, I can just even say M, lac M. LAC. I know that LAC, lactate dehydrogenase, aspartate aminotransferase, creatine kinase, they will cause myocardial infarction. Sometimes they can ask you to write these names. They just say the diagnostic enzyme which should be present for myocardial infarction are, and they want you to list all of these. Now, for enzymes, you also know that there are multiple factors that affect the rate of enzyme catalyzed reaction, and that includes temperature, hydrogen ion concentration, pH concentration, and also some other factors. But more specific, these ones. To start with pH, enzymes work well at optimum pH. So below the optimum pH, they are not that active. Okay, they are less active. In other words, they are inactive. Now, beyond the optimum pH, they are not inactive, but they've been destroyed. They are denatured. That's the same with temperature. Beyond 37 degrees, the enzyme is denatured. Below 37 degrees, the enzyme is inactive. On 37 degrees, that's the optimum temperature. That's where they'll be able to work very well. Now, for substrate concentration, look at the rate and substrate concentration. What happens that when you have got, let's say, 10 enzymes, when you'll be increasing the substrate, what the enzyme supposed to work on. Let's say you bring 5 substrates, the reaction will be increasing. 6 substrates, the reaction increases. When you reach 10 substrates, the reaction is still increasing. But when you exceed 10, the reaction will no longer exceed because all the active sites of the enzyme have been occupied by a substrate. So even if you exceed, you increase the substrate concentration, it will do no good. So that's why the reaction, the rate doesn't even speed up any longer. That is the same way with the substrate, the enzyme concentration. When you're increasing the enzyme concentration, the rate of the reaction will be increasing. But when you increase too much, so that the enzyme are too many in comparison to the substrates that you have, the reaction will no longer increase anymore because you have exceeded already the substrates which you have. Now let's talk about enzyme regulation. On enzyme regulation, we have got different inhibitors that can inhibit the way enzymes work or to regulate the way enzymes work. The first ones are known as competitive inhibitors, and I've seen this question came in your bio 1400. So competitive inhibitors actually bind the same site of the enzyme where the substrate is supposed to bind. That is where competitive inhibitors are going to be able to bind. Okay? That's where competitive inhibitors will be able to bind. Many drugs are going to act as competitive inhibitors of enzymes. So, for example, you have got methotrexate, and this one, I think, in last year's exam, they just got this exactly. Methotrexate is what type of inhibitor? So, methotrexate is a competitive inhibitor. It is a drug. This one, methotrexate, is a structural analog. What we mean by analog is that it looks the same. So it looks the same like tetrahydrofolate. Now remember we said tetrahydrofolate was a coenzyme earlier. So tetrahydrofolate is a coenzyme for the enzyme dihydrofolate reductase. And this dihydrofolate reductase is an important enzyme in the making of purines and pyrimidines. Those cytosines, adenines, guanines, thymines. So dihydrofolate reductase is important in the making of this. Don't worry, we'll talk about how you make purines and pyrimidines in detail as a topic. Okay, so what methotrexate is going to do is that it's going to be able to bind to the active site of this enzyme. So the coenzyme tetrahydrofolate can no longer bind to it because the enzyme is not having its coenzyme. It means that it can no longer work, right? So take note of this. Know the enzyme here, the coenzyme, and also the inhibitor. What kind of inhibitor is it? It is an active inhibitor. So now how can you reduce this kind of inhibition? When you increase the amount of substrate, you are going to be able to reverse this inhibition. Think of it like there's a competition between, so if you increase the tetrahydrofolate so that it becomes more than the methotrexate, there will be more chance that you are going to overcome the effect of methotrexate on the enzyme, and so the enzyme will be able to make purines and pyrimidines. You also have non-competitive inhibition. Now, non-competitive inhibition, you can have reversible or non-reversible. Reversible here, no competition between the substrate and the inhibitor. Okay, this is non-competitive inhibition. What happens is that the inhibitor doesn't bind to the active site; it will bind to the allosteric site. So even the substrate, it does not look the same like the inhibitor, because the inhibitor and the substrate, they don't bind to the same position. You can look at here the inhibitor, you can see where it is binding. It's binding on the allosteric site, while the enzyme the substrate is binding this side. So what happens that when the inhibitor attaches to the allosteric site, it will change this shape of the active site, and so the substrate can no longer be able to fit on that enzyme. So this one is reversible. You can reverse it. Now for the irreversible non-competitive inhibition, here the inhibitor will be able to bind to the allosteric site also because it's non-competitive. But then it binds more tightly, so you cannot reverse this. Silver and mercury ions. Now what happens is that these inhibitors will be able to destroy a function group of the enzyme, which is important for the activity. So because they destroy the active site, because they destroy the functional group of the enzyme can no longer function because you have destroyed its functional group. For example, the the medicine penicillin. Penicillin, what it does is that it will be able to act by covalently modifying the enzyme transpeptidase. So if it modifies the enzyme transpeptidase, it is going to prevent the synthesis of bacterial cell wall. Now, this cell wall of the bacteria, as we talked about, remember last time what we discussed, it is made up of these peptidoglycans which have got amino acids and carbohydrates. So those amino acids cannot form close linkages. Because of that, in other words, you cannot form a strong thing to surround the cell wall. So what happens is that the cell wall is no longer strong, so water can enter the bacteria and the bacteria will be able to burst. So that is penicillin. Okay, take note, penicillin is a irreversible non-competitive inhibitor. You also have aspirin. Aspirin is going to act by covalently modifying the enzyme cyclooxygenase, and that will reduce the synthesis of inflammatory signals. Now, aspirin is going to be used when, in case someone has been inflamed. For example, you have got an allergic reaction. I think, for example, maybe you've been bitten by a wasp or being stung. So to be able to reduce that we call that as an inflammation, ukfimba. To be able to reduce that, this can help. Okay. So what happened is that aspirin will be able to act on the enzyme cyclooxygenase, which causes inflammation, and that will be able to reduce the inflammation. Please take note of these two as examples of irreversible non-competitive inhibitors. At least also take note of the enzyme that they are working on. Now let's talk about feedback inhibition. In feedback inhibition, what happens is that the enzyme at the beginning is inhibited by the end product in a pathway. Often it is going to take place at the committed step in the pathway. Look at this. You had the enzyme here and its substrate. You can see the substrate, which is like triangle, and the enzyme. What happened is that when this reaction happened, the product after this reaction, remember the enzyme is not changed, only the substrate changes to being a product. So this becomes the first product, and this first product will act again with another enzyme it to form another product. This other product acts with another enzyme, it forms another product. Now this other product that you have formed will go and attach to the allosteric site of the first enzyme. When it attaches to the allosteric site of the first enzyme, it changes the shape of the allosteric site. And what happens? This first substrate can no longer fit. And so this reaction can no longer continue to happen again. Okay, so this is the feedback inhibition. There is also allosteric inhibition. So you have got allosteric inhibition and allosteric activation. So look at this. The enzyme binds to the allosteric site, it changes the active site, and then the substrate cannot fit. Allosteric activation is where you have got the activator. Now here it's not called the inhibitor, it's called the activator. The activator binds to the allosteric site, it changes the active site to make sure that the substrate fits. That is the allosteric activation. Okay, and then another thing that you need to understand is the proteolytic cleavage or zymogenes. Things like trypsin, these are enzymes, chymotrypsin and elastase. These ones are going to be produced as zymogenes. What we mean by zymogenes that they are produced while inactive. They are not active when they are produced. So what happens that when they are produced, they are going to be transported in their zymogen form, in their inactive form, and then they are going to be activated after you cleave or you break off some bonds, some peptide bonds, remember, because these are proteins. So trypsin is synthesized initially as a zymogen trypsinogen. You are going to understand this one in GIT physiology. So you are going to produce, what will happen is that the body will produce trypsinogen. Trypsinogen now be broken down to form trypsin. Now trypsin is the active form of trypsinogen, which is the zymogen. Okay. And this is going to be by the enzyme enteropeptidase. Activations that can happen is that after you have activated your trypsin can now cleave and activate further trypsinogen. Remember, you had produced trypsinogen, which is inactive. Trypsinogen was broken down by enteropeptidase, and it produced trypsin, which is active. Now, trypsin will further come and break trypsinogen, which is inactive, producing more trypsin, and and also producing other chymotrypsinogens and the proelastase like that. This is what we are showing here. You look, we had produced first trypsinogen on top here. Enteropeptidase acts on this trypsinogen, you produce trypsin. And then the trypsin can now get to work on a proelastase, producing the active form, which is the elastase, and also working on a chymotrypsinogen, producing the active chymotrypsin. So that is how these zymogens work like that. Okay, zymogen is just the inactive form. Okay, another thing we need to understand is the attachment of the inhibitory subunit. Inhibitory subunit. An example we use is the protein kinase A. You understand very much about protein kinase A as we go on with the course. So protein kinase A has got the catalytic subunit. Catalytic subunit is where the substrate is supposed to attach, so meaning it's inactive. Okay, now you can see in this case it is inactive. It is also having this region which is known as the regulatory subunit. So what will happen is that for this protein kinase A, CAMP is what activates protein kinase A, and this is a very powerful pathway that you are going to understand. Protein kinase A does not work until you have got CAMP, cyclic adenosine monophosphate. Cyclic adenosine monophosphate to be able to attach to the regulatory subunit of protein kinase A, and then the regulatory subunit to be able to disassociate from the catalytic subunit, and that now makes the catalytic subunit to become active. and then protein kinase A can work. You understand very much protein kinase is a very powerful and important enzyme in our bodies. There are also some covalent modifications that should be able to happen to these enzymes, and it includes the phosphorylation. Okay, phosphorylation is just the addition of a phosphate. So what happens is this: when you have activated your protein kinase A, now your protein kinase A, every time you hear of an enzyme being a kinase, it means that it adds phosphate groups to other compounds. Remember, protein kinase A, we also call it as pKa, protein kinase A. It is an enzyme which was inactive. What activated it was the CAMP. After protein kinase A has been activated, it can now start getting phosphate groups, adding them to other compounds. That is known as phosphorylation. Okay. You have also other enzymes which remove phosphate groups, and those we call them phosphatases. Kinases will add phosphate groups, phosphatases dephosphorylate or they remove phosphate groups. You also have adenylation, which is the addition of adenine, deadenylation, methylation, and all these other things. So these are some modifications that can be able to happen to amino acids. To some amino acids, some proteins can only work if they've got a phosphate. Others can only work if they don't have a phosphate. Others can only work when you add a methyl. Others will only work if you remove a methyl. That is why you can hear of these terms. So these modifications will cause a change in the tertiary structure of the enzyme. And so if you change the tertiary structure, it will be able to alter the active site of that enzyme, thereby either activate it or deactivate it, meaning that you can either increase its function or decrease its function. So there are some important ones that you need to know, and you need to know. Okay? You need to know. Especially these ones where you can see a star. For example, the amino acid arginine. The amino acid arginine will undergo a modification known as N-methylation and ribosylation. In other words, you are going to add a methyl and you can also add a ribosyl group. I don't know how you are going to know this, but you have to know because these are questions which come, especially where there are stars there. Also, arginine and asparagine are different. Asparagine will only undergo deamination, meaning you remove an amine group, and glycosylation. Okay, glycosylation. Take note, asparagine, glycosylation. At least asparagine, if you can say asparagine, it has got a G in it, and then glycosylation, it starts with a G. That is how you start mastering things now in med school. You also have the enzyme, the amino acid cysteine. Now you know that cysteine and methionine are the only two enzymes with a sulfide, with a sulfur, right? So these ones are going to undergo disulfide formations. You also have glutamic acid. These ones are going to undergo carboxyglutamate formation and methylation. Just try to take note of some of these, especially those which have been studied. Okay, might take a bit of time. Try to find ways in what will work best for you to be able to make sure that you know them. How about if you change optimal conditions? When you change optimal conditions, for example, pH, temperature, availability of enzymes, availability of substrates, what will happen? You are going to stop, you are going to reduce the way the enzymes will be able to work. The enzymes will not be able to work well because you have reduced their optimum condition at which they work. Okay, and the last concept I think here and most important one also is enzyme kinematics. Every time you hear of kinematics is how they do reaction, speed of the reaction, the rate of the reaction. And this is a very, very important. So we have got what is known as the Michealis-Menten equation. Okay? The Michealis-Menten equation. Michealis-Menten equation, there are some enzymes which obey the Michealis-Menten equation. Many enzymes, the rate of catalysis the rate of catalysis, we call it V. Okay, like that's a speed. You know that rate is just a speed. Now, because this is VO, it means that that is like the initial speed, isn't it? So the rate of catalysis is going to be defined as the number of moles of product formed per second, right? And okay, the number of products, moles of products formed per second, that is going to rise linearly as substrate concentration increases, and then begin to level as you approach the maximum at higher substrate concentration. What are we saying in this statement? What will happen is this: for most of the enzymes, the rate of the reaction is going to be able to rise linearly, meaning that if you increase the substrate concentration, you increase the rate. You increase substrate concentration, you increase the rate. Linearly, you can see this was almost a straight line. But then as you get to continue increasing the concentration of the substrate, you can no longer increase the rate of the reaction. Okay, and then you are going to reach a maximum speed for that kind of reaction catalyzed by that enzyme. So the maximum speed is known as Vmax. Vmax. Now, if you look at the maximum speed, say let's say for this enzyme, its maximum speed is 10 meters per second. The half of the maximum speed, that is going to be 5 meters per second. So that is known as Vmax over 2. Hope you are getting this. Half of the maximum speed is Vmax over 2. Now, that half of the maximum speed, if you come and find out the concentration of the substrate at half the maximum speed, that is known as the Km. So what is Km? Km is just the concentration of the substrate when the speed of the reaction is half of the maximum. That is what we call Vm. And this equation, you have to know it. 1 divided by the initial speed is going to be given by Km divided by the maximum speed multiplied by the concentration of the substrate plus 1 over maximum speed. This equation has to be known. Now, this is a linear equation. A linear equation. You know that a linear equation is given as y is equal to mx plus c. So for this reaction that you can see here, y is being represented by 1 over the initial speed, and that will be equal to the gradient. Now gradient, which is m, is going to be represented by what? Km divided by Vmax. And then the x-intercept to be represented by 1 over the concentration of the substrate. And then plus c. C is the x-intercept, which is 1 over Vmax. So you can actually write a straight line equation, and this is how it's going to be. You can see the gradient of the line is going to be represented by Km over Vm. The y value will be 1 over Vo, and everything like that. So this is the one that you can see here. So this is the y value, and that will be equal to mx plus c. So you can see the y value. The, the y-axis is being represented by what? 1 over Vo, right? 1 over Vo, 1 over initial velocity. And that will be equal to the slope, the gradient of this rate of this reaction is going to be represented by what? Km over Vmax. Meaning that if they give you the gradient, you should be able to determine either the Km or the Vmax. They'll give you the gradient with the Km, you can find the Vmax. Or they give you the gradient with the Vmax, you should be able to find the Km, right? And then the x value, the x-axis is going to be represented by 1 over the concentration of the substrate. That is why you can see this one here. And then the y-intercept is going to be represented by 1 over Vmax. This is the one that you can see. That's the y-intercept. And they can give you a question. On the double reciprocal graph, 1 over Vmax represents, or the x-intercept represents, or the y-intercept represents. So you should be able to know what it's representing. Okay. Do you have any question here? Any question? Nothing. Okay, good. Now, what is the importance of knowing Km? Remember we've said Km. What is Km? Km is the concentration of the substrate at half of the maximum speed of the reaction, or at half Vmax. So Km is the concentration of the substrate at which half of the active sites are filled. That's the meaning. Km is the concentration of the substrate at which half of the substrates have been filled. Okay, that is one thing that you need to take note of. The other thing is that Km is related to the rate constant of the individual step in a catalytic scheme. But one important thing, very important, that you need to know is that if K look at 4, a higher Km indicates weak binding, a low Km indicates strong binding. This one is, I need you to know this one. So if you find for a reaction that you have got a high Km, it means that that enzyme and the substrate, they do not bind strongly. But if Km is small, it means that that enzyme and the substrate bind very strongly. Okay. How about what is the importance of Vmax? The maximum velocity Vmax reveals the turnover number of enzymes, which is the number of substrate molecules converted into product per enzyme molecule in a unit of time. So, how many enzymes are you having? So, the number of enzymes that you're having will determine how many substrates you are converting to product. So, that is Vmax. Vmax is telling you the speed at which you are converting the substrates into products. Okay, so that is what I wanted you to take note of there. Now, not all enzymes. Now, allosteric enzymes do not obey Michealis Menten kinetics. They can give you a question. Allosteric enzymes dash Michealis Menten's kinetics. Obey, do not obey. Allosteric enzymes do not obey Michealis Menten kinetics. Why don't they do that? Because Michealis Menten equation can only work for those enzymes which have got only one subunit and one active site. Now, allosteric enzymes have got multiple subunits and multiple active sites, okay, for substrates to be able to bind. And so they are not going to be affected by the Michealis Menten kinetics. Corporate binding is sigmoidal and not hyperbolic. Okay. Take note of also this. The binding that you are seeing in this one, which we are talking about as the Michealis Menten equation, is sigmoidal and not hyperbolic. What do we mean by sigmoidal? I believe we know what we mean by sigmoid. A sigmoid is like an S. Let me try to represent that. Okay, so what we are saying is that the binding that we are talking about here is not hyperbolic, but it is sigmoidal. This is how they can ask you a question. They can just change the other statement. They say the binding is hyperbolic. So sigmoidal means that the graph goes like this and then goes like that. It makes like an S. Hyperbolic means that it goes like this. That's an hyperbola. So the reaction is not going like this for Michealis Menten. It goes like a sigmoid. There will be a point, the concentration, the reaction is increasing very much. When you increase the substrate concentration, there will be a point when you just stop increasing the rate of the reaction. Okay, so this is what we know, we call the double reciprocal plot. The double reciprocal plot, and they can ask you on the double reciprocal plot what represents the gradient, and I think we've already mentioned that and we have understood. Okay, so that is